Yeah, hello. So I'm Hannes, and I will talk about Mirage Operatings, which is a robust operating system designed and built from the ground up. So first of all, advertisement for your favorite operating system, which is Linux. Just turned 25 years old, so here's your cake. You know it. You have to go ahead and compile it yourself. So good luck with that. In the meantime, also, so Linux is one of the widely used operating systems, I believe, and it was actually designed for machines like that. So it's a bit old and a bit big because there are layers of legacy and so on. Or as some people might know, I'm preaching that Linux is actually built on sand, and here you can see what happens if you build on sand. So you can build any palace on sand, but it will sink anyways if there's enough water. So I think we are learning, and we are learning by, instead of using a full Linux for our services or so, we do something with containers because it's a new big thing. And I have to tell you, containers are a nice solution, but unfortunately they burn. So where are we? We are using 70s technology, which was never meant to be used in that way, still in 2016. Our systems get more and more complex, so it's not getting easier. It won't get easier anyways. We have several layers of legacies, so we build legacy, so we build our current systems on top of different layers of legacy, which means that we don't get rid of software, but we only increase ever the amount of source code. And in my opinion, we strongly need a rewrite of all of the basics and the fundamentals in order to think about what we actually want to achieve and what is there and what we don't need yet. So I claim, as Lisa also does, that the whole damn system is wrong. And please keep your coins. I really want to have change. So what is the general idea behind that, or what is my personal goal within my lifetime or so, is to have a system which I would claim Hive, because the name cloud is already taken in a different world, and this name cloud is nice, but it is wrong. So what I would like to have is a data store and communication system, which is not too difficult to imagine, but it should have, as a first-class citizen, trust network, which is then also used for resource sharing. And it should build on some federated approach, so I don't think that we can get away with having some sort of federation where each of your own hives is basically a set of machines or a hierarchy of machines. Yeah, regarding clouds, I here completely agree with that FSFE advertisement that there is no cloud, just other people's computers. So what are the requirements for such a hive I have in my mind? Well, it must be easy to set up, because I want to enable non-technical experts to install and run their infrastructure, their own. Obviously, you have multiple devices, which might be mobile phones or computers, laptops, or whatever. As I mentioned, you have some resources which you might want to share. So I could say, oh yeah, BornHack was such a great venue. Everybody whom I met, I just want to allow them to use up to 20% of my resources, which I have. Which should then also be a bit transitive, so you should give them away to someone else who's in deep need of that. Obviously, core of the whole thing is to have some federated group messaging, hopefully encrypted. I hope some people are working on that right now, right here. Then we have persistent data store. I mean, I usually want to have some data available, and I don't really want to manually care about backing that software, backing that data up and running my rsync to my other host manually. But somehow the persistent data stuff should just take care of that. I mean, there are algorithms out there. It can't be too hard. Yeah, short difference between centralized and decentralized. So I believe in a decentralized approach, but I think that the federated approach similar to used by email and so on is actually makes sense. Yeah, the trust network I already told you. You should be able to share resources also in a transitive sense. So you should be able to distribute those access tokens to resources to other people. And I would like to be able to say, oh, my friend Fu is able to receive presence updates from me. So when I switch the country, he gets my new phone number. So then it's not clear to me how you address stuff. I mean, you can use a hierarchical system, but then you need some initial, some centralized source of all the naming information, some centralized database. Might not be the right choice. Maybe a distributed hash table is better. And account verification, well, how do you get into that network is done by some initial key fingerprint verification or barcode scan. So that is what I have in mind basically. As resources we have storage, CPU and network load, so bandwidth. What are the properties of such an individual machine I'm talking about? It should be able to separate the concerns of the different services. There might be some services like web or something like that. There should be strong isolation between my data and your data. Obviously, if you back up your data to my nodes, they should be encrypted with something only you know. Also, if there are several nodes and they have some sort of locality like the same physical machine, they should use smarter ways for communication than TCP/IP. So they shouldn't need to use a network stack if they are on the same physical machine and they can just use a piece of shared memory. And each of those services should actually be only have the complexity it strictly needs. And as mentioned, some federation and group communication. But then I've been told that I should be more realistic and should cut down on my things. So let's talk about operating systems and operating system designs. So this, I just showed you where I want to be within the next 5 to 10 years. So what are the bigger goals of what I'm currently trying to do? But at the moment I'm more into the simple problems like designing an operating system. Mirage OS has been started, I think, 7 years ago in Cambridge at the university as a research project, and it was done by people who were involved previously also in the Xen hypervisor project, which was also a project started at the university and as a PhD of someone, and then was published later outwards, and there's now a company or several companies and people who actually use it. Mirage OS is a clean slate operating system written in OCaml, which is a programming language designed or developed in France, mainly available since maybe 25 years, used in both academic and industry. And it's actively developed. It is a compiled functional modular language. So you compile to native code, to native x86 assembly or so. and then just execute that. And the compiler is pretty dumb, or it's not pretty smart, so it does a translation, a pretty straightforward translation of the source code to the binary code, which means that you as a developer, you can already roughly reason how the binary will look like, and you pay as you go. So if you have allocations in your code, they will likely end up as allocations in the binary. OCaml allows you to write some sort of declarative code, so code where you can actually read the code and understand it. And the idea about configurability and complexity of system is that if you reconfigure your application or your operating system, then you basically recompile, so you don't really have the configuration as an external resource, but you can have that as well. So just to illustrate how much simpler a Mirage thingy, so a Mirage application actually gets. So on the left side, you can see the stack of the layers of a contemporary operating system, which is you have some hardware, usually use some hypervisor, some Xen or KVM or whatever you like. And then you have the operating system kernel, which consists of a scheduler and network stack, some file system implementation, some process implementation, some threads in the kernel, also user management. You have the whole file system has user permissions and so on. Then on top of the operating system kernel, you have a language runtime, which is not only the libc you have usually, but also the Python runtime if you, for example, write Python, or the JVM if you write Java code. Then you have the concrete application, which the logic you actually want to run. And that one depends then usually on configuration files, which are down in the file system. So in order to execute the application properly, you first need to have the configuration files around, they need to have the right permissions and so on. And in the Mirage approach, we just get rid of this whole operating system kernel, but we just use a set of libraries, and you link in only those libraries which you really need. So if you're, for example, having your mail server, or you have a mail server and you want to configure your mail server, you likely will not link in a scheduler and maybe not even persistent storage, because you store it in a remote database anyways. Then you certainly don't need a process management and users on the system, because why would you? I mean, you don't really need access control on that system, because anyone can just submit you mails and you just save them for further need. Obviously, those people who pop mail from you, so who receive mail from you, will need to be verified at some point by using either TLS certificates or something else. But you don't need a file system inside of a mail server. I don't think you really want to have a file system in a mail server. So the approach is to minimize the runtime and have just the runtime and the application code. We move away from having general purpose operating systems here, but we have a single purpose application. So for each of your different services, you just run a new virtual machine. You just run a new application, which you can start and stop. And this application does exactly one service. It also uses a single address space. There's no need for virtual memory in there anymore, because OCaml itself has memory safety, so you cannot access data outside of the bounds. And you don't end up in problems like double freeze or use after freeze. So in spatial and temporal memory safety is done by the OCaml compiler and runtime already. So we don't really need to duplicate that effort and do it via virtual memory. Virtual memory is also not needed because we only have one process. I mean, there's no such concept as of processes. So I think I've told you a bit why I think it is getting easier by just removing all the complexity, all the stuff we don't really need. So another example for the complexity argument would be a name server. And why should it need a file system or users or processes? It just basically needs a remote data blob or a compiled in configuration for the entries it should serve, or a link to a remote, maybe Git database or some other remote data blob, maybe an HTTP URL where it finds its configuration or startup information. And then by having that, by not having a file system, for example, you end up that it is much easier to configure, because you don't have to care about files, about permissions and user IDs for specific files, because you don't have any files. Runtime control can be done via anyway, maybe via a Plan 9 file system channel, or just no remote runtime control. You can secure your channels, so if you want to authenticate or if you want to exfiltrate data for which may be a logging service, so you might want to log whenever a specific host name is fetched. And that you can just do using syslog or some other protocol. And you can secure those channels by just using TLS and your very own certificate authority. The result in this name server, which is basically a prototype we have developed, the code size is smaller than 5% of a common Alpine Linux virtual machine thingy. And the virtual machine size here can be measured in kilobytes rather than in megabytes or gigabytes. So it gets smaller. And by getting smaller, you lose attack surface. And by using some program language which has some memory safety, you also you lose attack vectors. You get rid of attack vectors. So you get, in the end, both in the code size and in the code complexity, you have fewer potential problems. What is the deployment story of MirageOS at the moment? Well, it was initially developed as a Xen guess, so I think a PV guess, but don't cite me on that. I'm always getting those different modes wrong. But you can just deploy it as a Xen virtual machine, basically. So it's a statically linked Unix binary. You can also just execute it on Unix, on a usual Unix system, which then either uses a sockets API for the network stack or uses a tab interface. You can also deploy it on other hypervisors like Beehive or Xhive or QEMU or whatever you want, using then the virtual I/O protocol to map network devices and block devices and console devices into that. And then on Linux you have this KVM, maybe it is a hypervisor, maybe not. And there you can also just deploy it and deploy MirageOS there. This KVM backend and the Beehive Xhive backend has been only recently developed, so it's pretty new and full of bugs, obviously. But it already works partially. What is the current state of MirageOS? As I mentioned, it was initially developed maybe 7 years ago at the university in Cambridge. And currently it's in a state where we at least dog-feed it to ourselves. So the Mirage website is using Mirage itself, hosted on a Xen machine. And also I have 2 or 3 different websites. what we have there are some crypto libraries like TLS, including X509 authentication and so on. Off the records, currently one guy is also working on an SSH implementation. Then also lower level network protocols is what we basically have. So we have some sort of TCP IP, then HTTP, some DNS, DHCP, an IP implementation. Unfortunately, not a really mature IPv6 implementation, but one which is in its very early beginning. We have some user interface library which gives us the chance to do some terminal-based rendering. There's a telnet server implementation, so you can actually run on your remote unikernel or your remote Mirage application a telnet server and have a user interface. So there's no shell. We have a persistent store which is Git-like or based on Git. It's called Ermin, and it's a branchable store which is persistent. It also talks Git server and Git client, so you can just pull some remote Git repository into your memory and work on that. Then we have a Plan 9 implementation, which we can use to expose control channels, for example, or everything else. We have syslog as an implementation, so we can actually set up a log host and redirect the logs of all the different applications to a single thing. Some advertisement next year. I will again organize a hack retreat as done this year, where we were roughly 25 people in Morocco at the beginning of March to do some coding and get to know more people. So that will happen. I thought I will bring some nice pictures of the user interfaces we have. So here's some TLS sequence diagram renderer, which is all console based. But you can see we are full Unicode compatible, and we even have round corners around our boxes. So. Another one which is somehow used by more and more people is an XMPP client I'm currently writing, but yeah, that is also just to show that it is possible, and it also uses the technology we are working on. So it's also written in OCaml, has full Unicode support, uses the XMPP library and the OTR library I developed before that. And yeah, it also uses our TLS library, about which I want to talk a bit more now, which is NQSB TLS, which is not quite so broken TLS, which is a TLS stack written from scratch with two goals: to have it as an executable specification and as a TLS implementation. So by using different or a specific coding style, we want to be able to abstract away from that either or. So either it is a test suite which tells you how the specification looks like, or it is a concrete implementation you can run. We don't really want to have a model of TCP/IP of TLS, but we want to also be able to run it as an implementation, which is then certainly a TLS implementation is easy, but you need to get then the interoperability right, and once you have that right, you might want to think about speed, because I don't believe that if you are 2 orders of magnitude slower than everything else, that you have that you can get any piece of the cake. So what is the structure of TLS? Well, TLS is a family of protocols developed since 20 years or so, or 15 years at least. And currently they are working on TLS 1.3, which is a new revision which might be adapted within a time frame of maybe 5 years or so. So in the center we have some TLS library or module, which has here some state machine and some state logic. And that itself depends on some modules which are able to parse incoming byte vectors or to serialize and to serialize outgoing byte vectors. So we need to do some packet processing and buffering and so on. That is somewhere deep inside TLS. We also have some crypto library which has a pseudo random number generator, which is used by both the TLS implementation but also by the X509 implementation. The X509 implementation obviously needs to read and write ASN1 encoded fragments. And it needs to get its trust anchors at a configuration time option. So which are the CA certificates we should actually trust. And then this whole TLS library here, or this whole TLS module here, gets as an external dependency, so it doesn't call into something which is called a flow. A flow is just a structure which sends and receives data, so it is doing something which might be a different computer which you are talking to, but in the test case it can also be some hard-coded data, so some byte vectors which you have on your disk, or some piece of code which generates byte vectors. And so this flow module here, down here, it is not part of the TLS library, but it's in front of the TLS library, so we can plug in different flows, and the TLS library itself doesn't call into send and receive on its own, but it just gets a state transition. Well, the core of the TLS library is here the function handle TLS, which receives some state and some buffer. So buffer is some received byte vector or generated byte vector, and then it can transform itself either into the OK state, which is OK, and then it has a new state, and then a buffer which might be, well, maybe a buffer which is transferred to the higher layer, so the encrypted application data is getting decrypted and passed upwards. And then another buffer which is optional, which is a buffer to be sent to the other communication partner, so something like output. And the other potential result is a failure and transition. So whenever we receive data or whenever we get some byte vector or some buffer as input, we can also fail on that buffer because it might contain invalid data which we cannot parse and cannot handle, or which we cannot handle at this point. So this core fragment here is purely functional, and you can see that because the error handling is done explicitly, and it goes from state to state. So it receives an old state, and instead of mutating some values in that old state, it just returns a new state. So it allocates some data and returns that data instead of mutating the heap at all. Other things we can express in OCaml, which I think are pretty powerful, is how we do the state transitions of our state machine. So first of all, when we receive a piece of data and we are in the handshake, then the first thing we do is we try to parse the buffer which we received here. And parsing it may return again either an error or OK and a value. And if the parser fails, well, then the entire handshake fails for us. So then we just say, oh, we have a reader error, and we just terminate the connection because there's no reason there's nothing we can do if the incoming byte vector was not valid. But in the positive case, so if we have managed to decode the byte buffer or the byte vector we got as input, then we look, what is our current state? So what is our current, what is the message we expect as the next message? And if our current state, this is a service state machine here, is that we await a client hello, so the next one should be a client hello. And the past handshake is actually a client hello, which value here is ch. Well, only then we process that and return the potential return values, so in new states and maybe some message to be sent to the other side. The same is true for, well, if we await client finished, so if we are towards the end of the TLS handshake, and we already accumulated some session and a log, which is just a byte vector of messages, and we receive the finished message, then we really process that one and verify that it is properly signed, or the contents of it is a proper MAC, and return positive. And there are more things here which are good to do. But by default here, down here, by default we fail with an unexpected handshake. So in the default case, if we don't find a match, or if we are not in the right state for the incoming frame, then we just fail and say, oh, we expected some other message. So we use this OCaml type system to enforce some state machine invariance. I mean, certainly it is not a full proof here, but it is already an improvement over nowadays code. So about over, for example, the OpenSSL code, where you do the state transitions by mutating some data values. And it turned out last year, I think, that it was not always sufficient, or the Java stack was especially bad by having done way too many, or accepting way too many frames. I told you a bit about ASN1. ASN1 is the abstract syntax notation version 1, and it is a grammar how you specify key value trees. And in the specification of X509, there's one data structure which is called the to be signed certificate. So that is the inner part of an X509 certificate without the signature and Digest algorithm. And the to be signed certificate is just a sequence of version number, serial number, an algorithm identifier to be used as a signature algorithm, then an issuer, which is just an X500 name, a validity, which is from and until, then a subject, which is also a name, and a subject public key info, which is the RSA public key or the elliptic curve public key. Then optionally unique ID for the issuer and the subject, and optionally extensions. So this is how you can find it in the printed RFC or so. And we developed a domain-specific language to encode exactly that into OCaml. And if you look now onto the slides, you will see the small difference which we have. I will do that transition again. So you have to move some of the code if it's required or optional into the front, but basically it is very much the same syntax. And by developing that, we are pretty sure that we are able to encode the certificate as a sequence of structures. And this also generates, or this also is then the parser and encoder code. So instead of manually trying to parse ASN1 structures, we wrote parsers and generators for the primitives, and combinators like sequence for the combinatory structures. So we don't have to manually write parsing code when we want to parse new ASN1 grammars, but we just have to write the parsing code for the primitives, where a primitive is validity or version, well, or string and the different string encodings and so on. But this means that the developer of the X509 library doesn't need to know too much of ASN1, and especially don't need to keep track of the parser and in which state it is in order to get it right. And parsing ASN1 has been problematic in other TLS implementations as well. X509 validation, well, we do that also in a more or less stateless way. So we have our small predicates which can look whether a time is valid, which takes a time and a certificate, and just do the comparisons. Then validating the host name or the extensions and the server extensions. And only if all of those predicates are true, we return success. So instead of having to remember in some imperative code what we already have done, or so we try to express that in a single statement which fits within 10 lines, and we can actually understand that we did the right thing. So we at least check the right predicates, and then we have to definitely look into each predicate definition in order to look whether we did sufficient test for that. The cryptography which we implemented, well, the cores are written in C, but they don't use any advanced C features like memory allocation or data-dependent loops, but they are just the textbooks examples of those ciphers and hashes. And the reason for writing them in C is just performance, because in OCaml we have a garbage collector and we have only 31-bit integers by default. So that is not sufficient to do those 32-bit integer arithmetics on. But the higher level modes, so the cipher modes like counter mode, CBC mode, ECM mode, well, you shouldn't use that. GCM and CCM and so on, these are written in OCaml, which are then communicating with the core, which is block, decrypt, and encrypt. The public key crypto is written in OCaml, and we use a big number library, which uses in the backend the GNU multi-precision binary library, GMP. And the public key crypto itself also uses blinding on the OCaml layer, so we don't really need to have GMP doing some constant time operations. We also have a random number generator, which is Fortuna, which we also implemented in OCaml, once again using AES CTR from C. And we have some entropy collection, which is basically based on either CPU features or non-deterministic computations you can do with a CPU, as explained in the Whirlwind papers. Or we also feed from the main timing loop, so from the main scheduler we feed in some bits and bytes. What are the results of the Sol TLS library? Well, we are interoperable with most of the stacks. Our code size is roughly, well, maybe 4% of other implementations. We also had some fun and developed a service, which is the Bitcoin Pinata, which we put basically beyond our TLS stack, so we expose the client and the server side of our TLS stack. You can even use Netcat to short circuit them. And if you properly authenticate either as a client or as a server towards that service, then you get the private key of a Bitcoin wallet, which is filled with 10 Bitcoins. And we have that, I mean, we also here have the long disclaimer that we A, trace users, and B, that we cannot derive any security out of it. But we have it online since 1.5 years, and it is also written in Mirage as a Mirage OS application, and it is a small virtual machine image running on Xen somewhere on the internet. This is actually a picture of the dependencies, well, of the libraries which are linked in here. So you can see actually, you can actually render a graph with all the libraries which are involved, and the graph is not exploding. So if I would try to develop a graph of the Linux kernel and OpenSSL running on top of it, I think it would explode. I mean, depends on the granularity, but it's very likely that it would explode. Yeah, I need to somehow where do I get my data? Yeah, reboot, maybe. So now I should be able to load that again. There we go. This is another visualization which takes into account the sizes of the different libraries. We can see that libgcc is here the biggest contributing factor towards the binary size, but that one also, we got rid of that basically. Just a helper library which you need on some system which don't provide some 128-bit primitives. What is the result? Well, it's up since more than a year and still up, and nobody has hacked it. I found actually a bug in our whole stack which allowed me to steal my own bitcoins, but that's a bit pointless. And yeah, we cannot infer any security. And why did we do that? Well, Bitcoin has some sort of transparency, so everybody can look whether the bitcoins are still there or not. And that is what we thought would be nice to have there. A bit about performance of our TLS stack. The handshakes, so the asymmetric crypto operations, are roughly the same speed as other implementations. And the throughput is interestingly better than, for example, Polar SSL, but up to 85% of the speed of OpenSSL. It surely depends on the block size you use, and then you can measure the throughput in megabytes. But 85% of the speed of OpenSSL, I think, is a good, this is a high value. What do I have here? So to rehearse, we have a stateful protocol. Well, how to implement stateful protocols, and the idea is to have a purely functional core which goes from state and input to state and output, to have explicit error handling like error monad or result type, and especially don't use exceptions or so. And the behavior of our core protocol logic is only dependent on its arguments, each function, but not on arbitrary memory out there. So there's not a class field which you can mutate in some method and you read from, and depending on the value of that class field, we have certain behavior in the sorting or whatever. That is not the case, so we try to have the code very local, and that you can actually locally understand the code by just looking at the input arguments and looking what is returned. We isolate the side effects like timers, input-output, mutable state, which is then giving an effectful layer on top of the pure protocol logic for the side effects. And now I have to cheat a bit because my presentation was somehow broken. Let me go to the end of the overall talk, where I want to conclude that my main goal is to enable people to take control, to take back control over your own data or over their data. And everybody should be able, in my opinion, to have full control over their data. I think it will change the future of how we use our computers, because nowadays a lot of people go to Google or Facebook or whatever because they provide nice interfaces, but also people then give control away over their own private data. Mirage OS itself is an active open source and research project. It is engineered, I think, with a very radical approach, at least in the systems community, to just throw away all those layers of POSIX and all the other crap. And it avoids several root causes of exploits and problems in computer security by just have a decision on a memory safe language and composable libraries instead of having all the complexity in a general purpose operating system. So we have a pretty small trusted computing trusted code base. It's maybe 2 orders of magnitude smaller than a Linux system or so. And we have, I think, reasonable performance. And that's it from me. I'm happy to answer questions. Yes.
Which is kind of the most horrible 80s technology you can imagine. Yeah, that was just more or less an observation.
Yes, maybe. So, I mean, I think that ASN1 has solved a lot of issues which people are now trying to resolve with XML and JSON and so on, because it is just an encoding. And you can send ASN1 also as a packed encoding over the wire, which then is very small. You save a lot of bits doing that. And ASN1 is crucial to nowadays this X509 land and the TLS. And what I see is in re-implementing stuff, I don't want to re-implement old crap, but I still want to be able to communicate to other parties. and I can get rid of things like well, hopefully IPv4 soon, but unfortunately not right now. But on
But in your TLS stack, you seem to implement a lot of stuff that many people already consider deprecated, like CBC mode or.
yeah, maybe stream and CBC mode is already deprecated, but we did some experiments and we don't talk to maybe 5% of the internet because we don't implement SSL version 2 or SSL version 3, and we require them to have some renegotiation features like secure renegotiation. And we can, I mean, the question arises, when will we finally drop support for stream and CBC ciphers? And the answer is hopefully once 1.3 is out and we can just get away with that. On which layer? So on the CBC mode, there's this lucky 13 attack, and we currently don't mitigate against it. Well, you can. So what does constant time mean? It is basically that you don't do any data-dependent branches, and that you do in, well, if you don't do any data-dependent branches, you should be fine. Maybe you also need to have the same memory access pattern in all branches, and or your result, well, you just have somewhere some bit to know which piece of result you would use. So in theory, you could apply the very same countermeasures as they have been implemented in C for Lucky 13. But it was just a big convolution of our code, and we decided to not yet care about that. And there was even a student in San Diego at university who tried to implement the Lucky 13 attack against our stack. And his results didn't really look promising. I mean, he wasn't able to find any bits in the key. So as soon as someone successfully exploits the Lucky 13 on our stack, I will go through the code and do it in constant time. But it's hard. I mean, it's...
You could also disable it.
Huh?
You could disable it.
Yeah. Yeah, likely I will just disable the CBC crap then.
Your idea of like reducing the complexity by having your idea of reducing the complexity inside your Mirage OS VM still leaves open the question like how do you consider the host operating system and how complex is that, and at the moment it's basically a Linux, right?
So at the moment we are on the the host operating system is either Linux or something else which provides a DOM0, or a Beehive host, which means it's FreeBSD or macOS 10 soon with the Xhive.
Not your vision for the future, but only like an intermediate step. And
That is currently only an intermediate step. What do I need from the host system? Well, certainly I don't want to write device drivers or too many device drivers, because it's hard and a lot of work, and all the Linux people have already done that. But apart from device drivers, I don't really need much. I need a scheduler which schedules the different virtual machines, and then I need something which does the memory allocation in the host system, or does updates to the page tables. So it's not too much I need in the host system. Nevertheless, currently it's still a Linux, a full Linux at the moment. What we especially don't need in the host system is networking, apart from a bridge which just bridges it to all the virtual machines. And the idea to get rid of that is, maybe in 10 years or so, when there are enough device drivers. So we also have one backend which runs OCaml directly on the Raspberry Pi, for example, and then we don't use any host system, so it's just on the bare metal. But there we are in the need of drivers, and we don't have drivers apart from a VGA frame buffer device. So it's a bit pointless at the moment. We are not enough people to actually do device drivers yet, so we just rely on the Linux ones.
One more question.
So in the, you mentioned that for no parts you wrote in TLS, there were some parts you wrote in C. Have you considered implementing those parts in Rust for like the future?
Yes, but I don't really want to have. So I mean, we have a small dependency on C because the OCaml runtime is partially written in C itself, but we don't have a dependency on Rust at the moment. So I'm only happy to write it in Rust or inline assembly actually once we have the OCaml runtime as inline assembly or as Rust code. Because I mean, we use C not as a C language, but we basically just use a mnemonics for inline assembly for the AS routines as well. So.
So you don't actually do memory allocations?
No memory allocations in C. That's too hard for us.